I'll hand over to Paul and William. So over to you, Paul and William.
Okay, thank you. Today I want to focus on linear regression, and I want to look at it, or actually two different uses of it. So we're going to talk about multivariate models, what we mean by an interaction, and then I want to focus on predictive modeling, what I refer to as predictive modeling. I have just a couple of slides to talk about multivariate models and what we mean by that. And then I want to look at regression, doing hypothesis testing with regression. And then in the second hour, I want to go through an example of a study that we did recently and look at some of the complexities of developing a predictive model with real data. So as you recall from last week, when we talked about linear regression or general linear models, we're talking about looking at means. So our dependent variable or outcome variable is a continuous variable. And when we do what's called ordinary least squares regression, we're basically looking at the dependent variable as a function of some independent variable or covariate or a set of independent variables. And so we looked at a couple special cases of linear models where if we have just a simple linear regression where our x variable is a dichotomous variable, which we will code either 1 or 0, that's essentially a t-test. And then if we have a set of independent variables that are all dichotomous variables, or maybe categorical, maybe they have more than 2 categories, then we have what's called a factorial analysis of variance. And then if we have a mix of categorical variables and continuous variables, then we call that analysis of covariance. So a distinction that I want to make these are sometimes used interchangeably in the literature, but they actually in statistics have a different meaning. When we talk about multivariable regression, we're talking about one outcome variable, and we have then potentially multiple independent variables or multiple predictor variables of our outcome. When we talk about multivariate regression, what we mean or what is meant by that is we have multiple dependent variables. And I'll give an example of that. So that's referred to as multivariate analysis of variance. And then we need to, when we talk about linear regression, doing an analysis of variance, or we need to talk about the concept of an interaction. And what is meant by interaction in linear regression is that the effects of one independent variable are not the same across levels of another independent variable. If they're the same, then we have what we call a main effect. There's no interaction. And then we can have, there's a couple of different kinds of interactions, what's referred to as an ordinal interaction or a disordinal interaction. And I have just a couple, or just a slide here of just examples. So if you have no interaction, what you're going to see if you have comparison groups and over time or some other variable like age maybe, the lines will be essentially parallel. if we have what's called an ordinal interaction, then that's our starting point, or maybe our ending point. Our comparison groups are essentially at the same point or very similar, start out at similar values, but then they digress in at different rates. They may not necessarily be, as I've illustrated here, one increasing, one decreasing. They might both be increasing, but they're increasing at different rates. And then the disordinal interaction means that they not only do they end up at different places, but they start at different places as well. So this is what we mean by an interaction in linear regression. And if the interaction is significant, then the main effect can't be interpreted directly. Now, that's generally true, although if the interaction is significant, maybe the main effect can be interpreted, but it can't be interpreted apart from the significant interaction. Usually we look at two-way interactions in linear regression. And if we, theoretically, we could look at any kind of n-way interaction, but then it becomes really difficult to interpret. And usually you don't see more than two-way interactions in the literature. Even getting the three-way interaction gets really difficult to interpret. And if you have like a lot of different variables and you get to like a four-way interaction, then it's almost impossible to interpret. So I want to go back to our cholesterol variable that we looked at last week, and we looked at the linear relationship between cholesterol and age, or age as a predictor of cholesterol. But in that data set, we also had a variable, the weight in kilograms. And so what we're going to do now is we're going to look at both age and weight as predictors of cholesterol. In other words, we're going to have a multivariable linear regression. And as you recall, or if you don't, you can go back and look at last week's presentation. We looked at cholesterol as a function of age, and we had a regression equation of 102.6 plus 5.3 times age, which we interpreted as for every year increase in age, the level of cholesterol goes up by 5.3 units. And so what I've printed out here is the output that you get when running this, this regression. Now, the format that you see it in here might be different, or probably is different from what you'll get running it in Python. But I want to go over the essential elements of regression output. And so you see that our first table here has SS, which stands for sum of squares, which you remember last year I went through how we can partition the total sum of squares into the regression sum of squares and a error sum of squares, or a residual sum of squares. And so here we have the sum of squares due to our model. In other words, sum of squares due to the impact of age on cholesterol. And then we have our error, or our residual sum of squares. And then we have a degrees of freedom associated with each of those. And if we divide the sum of squares by the degrees of freedom, we get what's called a mean square, or in other words, that's like an average sum of squares. And so if we look at the model sum of squares divided by the residual sum of squares, we get an F statistic, which, if you recall, that's one of the theoretical distributions in hypothesis testing. And so an F distribution actually has two sets of degrees of freedom, one for the model and one for the residual. And so that's why you see here an F with 1 and 23 degrees of freedom. And if you divide the model sum of squares by the residual sum of squares, you get this F statistic. So the 53.96 here is 101,932 divided by 1888. And then we can look that up in a distribution table, or do it you know, in a program that gives us the probability. And so here the probability of this F statistic being less than or equal to the 53.96 is very, very small. So we have this is our p-value here for this particular analysis. But in doing predictive modeling here, so we're looking at cholesterol predicted by age, what's really important to look at is this R squared value. And you remember from last week, the R squared was the sum of squares regression divided by the sum of squares regression plus the residual sum of squares. And so the R squared value we interpret as the percent or the proportion of variance that are of variance explained in our outcome variable, in this case cholesterol, by our independent variable, in this case age. So here you can see that it's pretty high. So we have 70% of our variance in cholesterol is explained by age. And there's also in most outputs, they do an adjusted R squared. What they mean by that, this is adjusted for the N. So if you have small n, this is usually going to be less than the actual R squared. As the number gets really large, then it's not going to make much difference here between the R squared and the adjusted R squared. And then there's this root mean square error. And this is just the square root of the error sum of squares, or the residual sum of squares. So this 43.46, that's just the square root of 1888. And then the second table is our regression table with our regression coefficient, the constant. And so you can see here that we get our constant at 102.6 and our regression coefficient of age of 5.3. As we've said before, that tells us that for every 1 year increase in age, cholesterol goes up by 5.3 units. And then the regression coefficients, we can test for statistical significance by using a t distribution. And so you can see here, this is the probability, the p-value for each of these. So obviously age is a significant predictor of cholesterol in our little data set here. And then we have the 95% confidence interval for the regression coefficient and for the constant. And what we see here is that if we have a statistically significant coefficient, then the confidence interval is not going to include 0. If it does, which will likely happen if we get a non-significant p-value here, is that this confidence interval will go from minus something to plus something, which tells us that it includes 0. So that means that from a statistical standpoint, the regression coefficient here is essentially, or is statistically 0. But in this case, neither one includes 0. So what this tells us is that in the population, our regression coefficient for age could be between 3.8 and 6.8 if we were to do an infinite number of random samples. And that 95% of the time, this interval would include the true population regression coefficient. So that's our simple linear regression model. And so what we want to do now is we want to look at a multivariable model, that is where we have more than one independent variable. And so we're going to look at cholesterol as a function of age plus weight, but then we can also look at age plus weight plus the interaction of age and weight. And so when we do that particular model, this is what we get. So we have the same table here with our sum of squares, our mean square, our average variability related to our model, and the average variability related to the error or the residual. And just as we had the F statistic, the probability of F, and then again, we get the R squared values. So now this is where we can determine whether adding weight to our regression equation really adds anything or helps us better predict cholesterol. And so you can see that the R squared, excuse me, is essentially the same as before with just age. It's about 70%. It's a little higher, but not that much. And then if we look at our regression table, we see that the regression coefficient for weight, 0.42, is not statistically significant. And then over here, you can see that the 95% interval includes 0. So this is telling us that weight probably doesn't add much to our prediction of cholesterol, because our R squared hasn't changed very much. And we have a non-significant regression coefficient for weight. If we kept it in our regression equation, then this is what it would look like, would be the constant plus 0.42 times weight plus 5.22 times age. And you notice that our regression coefficient for age didn't change very much. From just age by itself, it was like 5.23. Now it's about 5.22. So weight isn't really making much of a difference in our prediction equation of cholesterol. And there's actually a statistical test you can do to see if the change in R squared is statistically significant. From my perspective, this isn't probably really worth the time to do it. You just eyeball what it is, and you can tell whether it's making a big difference or not. So like if this R squared had gone up to 0.8 instead of 0.7, then weight would have been having a real impact on our prediction of cholesterol, and we would have probably found a significant p-value here for the regression coefficient and kept weight in our model. But because the R squared hardly changed at all and our regression coefficient was not statistically significant, we can go with the simpler model of cholesterol as being a function of age. So what if we look at the interaction of weight and age? Then if we add this, put this in our model, well, we have the same way of interpreting here whether there's a significant interaction. And so again, we'll look at our R squared value, and we see again that it didn't change very much. It's still about 0.7, maybe 0.71 now instead of 0.7. So that hardly changed. And then our interaction here is not, whoops, let me go back here. is not statistically significant. So we can conclude that there's no significant interaction of weight and age. That is, weight isn't changing with or isn't different with different ages as far as predicting cholesterol. So we then conclude that our best model is cholesterol just as a function of age. Okay, so then the next data set that I want to look at is our blood pressure data set that we had last week. We looked at the distribution and used our blood pressure for as an example for a simple t-test. But here I've added some additional variables. And so what we want to do now with we want to have a linear regression model. We want to build a linear regression model, but now our focus is on hypothesis testing, not particularly predicting blood pressure. And so we have a variable here, drug, that I've just called drug A and drug B. And how I've coded those is drug A is equal to 1, drug B is equal to 0. And so in addition to our two groups here that we're interested in comparing with respect to lowering blood pressure, are age and sex. Age, again, is in years. Sex, because it's a dichotomous variable, we've coded it 1 equals female and 0 equals male. So this design we would call a non-randomized comparative effectiveness. And our outcome, in this case, diastolic blood pressure, obviously is a continuous variable, so we're going to do linear regression. And our research hypothesis then is drug A superior to drug B in reducing blood pressure. And then conversely, our null hypothesis would be that there is no difference between A and B with respect to reducing blood pressure. And the reason that that we have age and sex in here is because we have a non-randomized study. If we if we had a randomized study, then we could just directly compare A and B with a t-test. But because it's non-randomized, there might be some other variables that affect blood pressure or confound any difference between drug A and drug B. So the first thing that we do in this case is, well, and actually really any case, you want to look at the covariates or the in relationship to your primary variable that you're interested in. So in this case, we want to look at the distribution of males and females in drug A and drug B, and we want to look at the distribution of age in drug A and drug B. So you can see that there's not an equal number or equal percentage of males and females in drug A and B. It's kind of reversed. So in drug A, there are about 55% are females and 45% are males. And in drug B, there's a smaller percentage of females than there are of males. So we have some difference there. And so you can see that in a non-randomized study, you likely get differences like these, whereas if we had actually randomized to drug A and B, this should have been pretty much equal. And then in age, we see there's quite a difference here. There's like an 8-year difference between the two groups. So that the patients or the subjects that are in the drug A regimen are about on average 8 years younger than B. So here we have two covariates, two variables that potentially are going to confound the effect of drug A in comparison to drug B. But this is sort of the first step in actually doing any studies you want to look at, just descriptive distributions of your covariates or your independent variables in relationship to your primary comparison groups. Okay, so as I mentioned, there's potential for selection bias. So the question that we would ask, maybe are drug A patients older than drug B patients? Well, we saw that that they're actually younger than drug B patients, quite a bit younger. And so in our regression model, we're going to include age, sex, and race, but we could include other factors as well. So maybe we have a study where we want to look at some comorbidities and their effect on the outcome, like diabetes or hypertension or something like that. But for our model, we're just going to look at age and sex. And so our model is going to be blood pressure as a function of the drug group, which is what we're primarily interested in. But we're going to have to also include in our model age and sex, and then the interactions of drug with age and drug with sex, okay? Because those are potential confounders in our comparison of the two drug groups. So here is our output for our first go with the model. And so you can see that we have the results here that, and as far as the interactions, that's the first thing we want to look at is our drug by age and our drug by sex interactions. And so we can see that neither one of these are statistically significant. The confidence intervals include 0. So based on this, we can drop these from our model since they're not statistically significant. Now we also have an R squared associated with this model, but when we're doing hypothesis testing, our focus is really on what's statistically significant as far as our regression coefficients are concerned, not so much the R squared. Whereas if we're doing a predictive model, we want to predict a particular value, then our R squared is our primary statistic that we want to focus on, and whether that changes depending on what's in the model. So we're going to do another model. We're going to rerun it without the age interaction, and then we're going to rerun it without the sex interaction. Or maybe I did it the other way, I don't remember. But so anyway, yeah, so here is our model run without the drug by age interaction. And so we just include the drug by sex interaction, and we keep age in the model, but not the interaction of age and drug. And so we can see again that the interaction here is not statistically significant. The confidence interval includes 0. So we can conclude that probably we can drop drug by sex interaction. And then so what we're going to do next is we're going to rerun the model with the age interaction. And so now you see that we have a significant interaction. Also, our main effect for sex is significant, as well as the drug coefficient here is significant, indicating that we do have some difference between drug A and B. But because these are statistically significant, we're going to need to keep them in our model. So what we see here, that we have negative coefficients for drug and a negative coefficient for sex. And you can see then that in the confidence intervals here, that neither one of them includes 0. They're all on the negative side here. So how do we interpret this? If we wanted to predict blood pressure using this model, what would we have? We would have the constant here of about 84. Then it would be minus, say, 25, depending on the drug that we're A or B that we're interested in. So remember, we coded drug was 1 or 0. And there's a reason for doing that, because it makes it easy to interpret the coefficients. So if we're talking about drug A, then we see that what we would do is we would subtract 25 from 83 or 84 here for drug A. If it was drug B, then remember drug B is coded 0, so it would be minus 24 times 0 or 0. So we would have no effect here. And then with sex, you can see that we have a negative 3.35. So remember that we coded sex as 1 equals female and 0 equals male. So if we had an individual here who was in drug A group and female, that we would have 84 minus 24 minus 3.36, okay? And then if, to include the interaction, then if they were in drug A, then we would have an additional 0.23 times the drug code, which is either 1 or 0, and their age. So you can see if drug is B here, that's 0, so this would not be included. But if we had, say, an individual who was in drug A group, was female, then we would have this 80, our constant 84 minus 25 minus 3.3 plus 0.23. And that accounts for the interaction between drug and age. Okay, and again, we don't have particular interest in looking at the R squared here, unless this would be, near 0 or extremely small, say less than 0.1. Then we would realize that the model we have here isn't really worth much. As I say, when we're doing hypothesis testing, what we're primarily interested in here are the p-values for our regression coefficients. And so
Hello, Paul.
Yeah.
Yeah, not to cut you out, but I think there's a question from Feng Yang on the chat. There are a couple, but this is more relevant. So that.
Okay. So do you want to go back a slide?
No, so on the chat. So if you look in the chat, yeah.
Oh, okay. Okay. So when you have the drug by age interaction, yeah, oftentimes age is left in the model, but you don't have to, because it's accounted for in the interaction term. Now we do need to keep sex, in this case, sex in the model, but when you're looking at interaction terms, we typically don't need to include, in this case, age in the model, but we could. But then it then is going to be more difficult to interpret. But I don't know if that answers the question. But actually, what you can do is when you do this exercise, include age in the age, sex, and drug by age model and see what happens. Okay. Was there another one? Oh, let's see.
There are two, but
Oh.
those are from me. Yeah, so
Okay, the difference between prediction and forecast. Well, that's, at least in my mind, that's pretty much the same idea. We're looking at predicting an individual value when we do when our focus is on predicting a value, whereas in the example that we're doing now, we're really more interested in comparing the drugs than predicting an actual value for any particular patient. And let's see. Oh, sure. Okay. Yes. So the BIC and the AIC, the information criteria, yes, that's often used to determine which is the best model. The problem with automated statistical tests, such as either forward selection or backward selection, which I'll get to in next hour in my example, is that that's really an invalid way of selecting variables for a model. And there are a number of reasons for that. There's quite a bit of literature on that. But that's used in almost every statistical package, is the forward, backward selection, or backward elimination, forward selection. If you do use that, it's okay if you have a few variables. If you have a lot of variables, then it's not okay. Let's see, was there another question?
no, I think that's it.
That's it, okay.
Thanks.
Okay. So then what should we use? Is that related to model building, I guess?
I guess, yes. I
Yeah,
think
okay,
that-
so I'm in the next hour, I'm going to give an example of the more modern way of determining variable selection for predictive models. But for the time being, just realize that sort of the traditional forward selection or backward elimination have been shown to not be really appropriate. And the reason for that is that you're using p-values to determine what goes in and what goes out. Sure. So that's the thing about when you include interactions. If the interaction is significant, then it's possible that the main effect may not be, but that doesn't really matter. It's in looking at the coefficients, if the interaction is significant, then it doesn't really matter what the main effect, whether that's significant or not. And we could probably drop the main effect if we and come out with the same conclusion. But that's kind of one of the issues of when you start to look at interactions. You have to kind of be careful of what you or I guess be careful of how you interpret that and what it might mean. But let me continue here. And so in my model, then I have in my first table here, I have just the observed blood pressures between drug A and drug B. And so you can see that drug A is the better drug as far as lowering blood pressure by about 8 8 points. Okay, but here, because in our model we had effects related to sex and an interaction of age and drug, our predicted values, mean values, are different. So for example, if we have, say, patients age 50, then there's a difference between males and females. You can see the males have a higher value of for blood pressure. If we increase age to 70, you see that we have higher blood pressures here related to age, but we have about the same difference between males and females. But for drug group B, regardless of age, the average predicted blood pressure for females is 80. For males, it's 84. Now, to really understand this and get a picture of what's going on in our example here, what we do is we graph the predicted regressions. And so, it'll change here. Yeah, so there we go. So here are the predicted regression lines from our model that has drug as a function of age, of sex, and age by drug. Okay, so you can see that for drug A, we have the effect here on blood pressure increasing with age. Okay, but for drug B, we have a constant basically across regardless of age. Okay, so these represent the means that I had in the previous table. So our conclusion here, which turns out to be a little more complicated than just is there a difference between drug A and drug B? Well, it depends on age as far as drug A is concerned. So you can see that with increasing age, the effect of drug A kind of disappears or starts to wane. So, but with drug B, it's higher than the overall level is higher than drug A, but it's constant across all age. It's unaffected by age. And so our conclusion might be, rather than just, drug A is better at reducing blood pressure than drug B, we would say that it's better than drug B for the younger patients. But as a patient is older, then the effect of drug A begins to disappear and become fairly similar to drug B. So that's looking at the interaction then between the drug and the covariates in a non-randomized study, and why you sort of need to really kind of, in a non-randomized study, really think about the effect of the covariates. Now, if as I say, if it had been a randomized study, we could have just, that would have supposedly washed out any differences related to age and sex between the two drug groups, and we could have done a t-test. Let me go back one slide here. So we could have just done, if neither interaction had been significant, or either the main effects of age and sex, then this would have been the comparison we would have done with a simple t-test and concluded that drug A is better than drug B. But it is better than drug B, but it's better for younger patients than it is for older patients. Okay. So I want to just mention briefly here multivariate analysis, where we have multiple dependent variables now. We can have multiple independent variables, but the difference here is that we have multiple dependent variables. In other words, we have patient has the same patient or the same subject in our study has different outcomes from maybe the same survey instrument, or maybe the repeated measures. But the example I want to give here is comparing mitral valve repair with mitral valve replacement. And so we did a study some years ago looking at quality of life or health quality of life using the SF36 domains, which have 8 different domains like physical function and so on. And so this is multivariate because we have 8 different outcome variables rather than just one outcome variable. And so what we want to do is we're going to do what's called profile analysis. We want to test the profiles of the 8 domains from the SF36 by our 2 independent groups here, repair and replacement. And basically what we do is we test for the interaction between profile and group. And if it's not significant, then we can interpret the group main effect as differences between profiles. And so this is what we, these are the domains of the SF36, measuring different things related to physical, social activities, general health, pain, and so on. And so this is what we get actually doing 3 different measurements at baseline, 1 year post-surgery, and then 4 or more years post-surgery. And so you can see that what we have here is essentially parallel profiles. In other words, we have pretty much the same profile, except at baseline and 1 year post-surgery, the repair group has higher scores. For the SF36, higher scores mean better quality of life, have higher scores than the repair or than the replace group. But as far as the domains, they look pretty much, or the difference here is pretty much parallel across the domains. And the same thing for 1 year post-surgery. But at 4 years post-surgery, we see that we still have essentially the same profiles, but now there's really no difference between the groups. So this was actually quite a complex interaction because we looked at not only differences in profile, but differences over time as well. But this is an example of profile analysis where you have multiple dependent variables. Okay, so I'll stop there with that portion. We'll take, I guess at this point, a 10-minute break. And then when I come back, I'll spend the next session looking at a particular study that we did as far as coming up with a predictive model and just the complexities that were involved in that.
Yeah, so Paul, I think there's a follow-up question from Finza in the chat. So we can address that after we come back, or you can look at that before we go.
Okay. Okay, so we'll come back then about noon, right at noon.
Okay, thank you. Yeah, so we'll see you all at 12 noon. Paul?
Yeah.
Yeah, so maybe you want to turn off your camera? I mean, you can leave it on, but in case you didn't know it's on.
Oh, yes, I forgot about that.
Yes, please. Because considering the session is being recorded.
Let's see.
It will be at the bottom of your screen next to your mic. Yeah, so your mic is off. Exactly. Good. Thanks a lot. And we'll see you when we get back. And to everyone, please note that this session is being recorded. So, thank you.
Okay, so are we ready to begin again?
Yes, Paul.
Yeah.
My screen disappeared on me. Sorry for that.
Okay.
Yeah. So yeah, we're back. We have 29 participants. We didn't lose anyone. So
Okay.
yeah, go back to it. But there is a question from things Zia, if I pronounce your name wrong. Sorry for that. But yeah, there's a question in the chat.
Okay.
I think Dr. Paul already explained.
Oh, okay. Okay.
Yeah, okay.
Thank you.
Let me just say a couple of things about the previous discussion. So I try to differentiate, the purpose of your study. So if you're just looking at a predictive model, then the primary statistic you want to look at is the R squared. That is the percent of variance that's accounted for by the variables, the independent variables in your model. The variance that they account for in the dependent variable. And it's possible that you can have variables in your model that the regression coefficients are not statistically significant, but if you take them out, then the R squared drops or is reduced significantly. So it's not always a particular regression coefficient for a particular variable in that context is not quite as important as when we looked at hypothesis testing. And so when you do hypothesis testing for non-randomized studies, then you really need to look at whatever covariates you have to see if they're affecting the difference between your comparison groups. If you have a randomized study, then randomization basically washes out differences between the two groups, and so you can just do a direct test. I'm going to do like a summary and overview tomorrow about what we talked about, so I'll go over that again tomorrow. Okay, so what I want to do next is look at a particular study that where we developed a model of predicting atrial fibrillation. And so this came from data from a registry, hypertrophic cardiomyopathy registry, or HCM. And so the focus here was predicting atrial fibrillation from a set of covariates or models. And so there were a number of issues in this study that we had to address in doing the analysis. And I wanted to use this as an example of, I guess, maybe a really complex analysis, or what turned out to be fairly complex. Every study you do might not be like this, but just to give you an idea of what's involved in data analysis, that is not just setting your data up and running a statistics program and getting an answer. So the issues that we are going to look at here are issues related to missing data, how we select variables for our model. Because our data is time to event, then we have to look at the phenomena that's referred to as competing risks. And in our survival model, or time to event model, I mentioned the Cox proportional hazards. So in this case, we have to deal with non-proportional hazards. We actually have multiple events because, as you obviously would surmise, that patients can have more than one AFib event over a certain amount of time. And then once we get a model, then we have to look at how well the model discriminates, how well it calibrates, and give some sense of whether the model is valid or not. So to start out with, our hypertrophic cardiomyopathy was an NHLBI sponsored study, and it was recently published in the Journal of the American College of Cardiology Electrophysiology last year. So the registry included patients with a diagnosis of hypertrophic cardiomyopathy. The age range was 17 to 67. Many of the patients were fairly young because HCM does affect younger individuals, probably more than older individuals. So we enrolled patients from 2014 to 2017. We ended up with 2,755 patients in the registry. These patients came from 44 different healthcare institutions in 6 countries in North America and Europe. Follow-up is actually ongoing. The study is not finished yet. We're at, actually, I think right now we're over 4 years of follow-up, the average follow-up. And the primary outcome that we're interested in is sudden cardiac death. Now, fortunately, I guess sudden cardiac death is not a real common occurrence. So in order to do the analysis, it's going to, of that particular outcome, it's going to take a while to get enough events, for enough events to occur. But a secondary outcome that is of interest is atrial fibrillation, or AF as it'll be abbreviated. So the first issue that we had to deal with is missing data. And anytime that you do research involving human patients or human subjects, you're going to have missing data. It's just, there's just no way around it. But the issue is that missing data may influence the results of a study. Now, if you have 1% or less of a sample that has missing data, then, or some people say if you have less than 5%, then just drop the missing data from the analysis. It won't make that much difference. And that's probably true. But if we have a fair amount of missing data, then we may need to do what's called multiple imputation to produce complete data sets for our analysis. Now, if you have a study where you've got 40 to 50% missing data, then even doing imputation is kind of questionable. In large studies like this, every effort is made to obtain the data, to get the data, but it's just impossible to get complete data when you have large studies like this. So we need to consider the reason for the missing data. And so we have different categories of missingness. And the first one, what's known as missing completely at random, means that missing data is not related to the outcome or any of the covariates or independent variables in your study. That's pretty rare to actually have happened, but anyway, if you have missing completely at random data, then you can ignore the missing altogether, regardless of how much there is. Then the concept of missing at random means that missingness or the mechanism of missingness is not related to the outcome, but it might be related to the covariates. So for example, you might have missing data is related to maybe age or maybe gender or something like that. And then the last category, not missing at random or not ignorable, means that missingness is related to the outcome and probably to the covariates. Now, the thing about dealing with missing data is that you really never know for sure which is the correct assumption. However, if you're assessing an outcome longitudinally, then it's not likely that your missing data is missing at random. So an example that I think I talked about last week, the Courage trial, where we assessed quality of life at baseline and then up to 12 every 1 month, and then every 3 months, and then 6 months at 12 months, and then yearly thereafter. So, and it turns out that some patients were followed out to 6 years or 72 months. And so what happens is that you have fewer responses to your quality of life survey over time. And what would be the most likely scenario is that over time, the patients who are less well are going to drop out of the study. Patients are going to die. And so over a long period of time, you're going to have the healthiest patients that are likely responding to your survey. And so in that case, it's the reason for there being missing data is not ignorable, that it's related to a patient's health. But we, like I say, there's no way of being certain why data is missing. But when we do the analysis, if we do have missing data, then we're going to have to make some assumptions. And so in this particular application here, we assumed that data was missing at random. I'll give some examples of that, of why that may not be entirely true. But anyway, what we do then is we're going to generate some complete data sets. And typically 3 to 5 is the number that's been kind of arbitrarily established as how many you need to do. In some cases, you might need to do more. But we're going to impute the missing values, and we're going to basically do that by regression, so that we have a certain number of complete data sets. Then what we do is we analyze whatever our analysis is, each set individually, and then we're going to combine the results to get estimates of our regression parameters. And so the regression parameters, whether we're doing simple linear regression, or in this case, we're going to do Cox proportional hazards regression, we just average each parameter over however many analyses we did. However, when we compute standard errors, we have to take into account both the variability within each data set and variability between data sets. So that's a little more complicated, but because we're imputing missing data, that is, we're estimating what the missing data might be, we have to account for both within and between variance. So there are different ways of doing this. What has been done in published studies, which is not a good idea, is just to do what's called simple imputation or single imputation, where you submit like a mean value, or you substitute the mode if it's categorical data. That's not a really good idea. What we used in this study was for our continuous variables was predictive, what's called predictive mean matching. And basically what this does is we make random draws from the observed values that are not missing, and then we substitute that particular value into the missing. And so you can see why we're doing this several times, because when we draw at random from the observed cases, we're not going to get the same value every time. But the one thing about predictive mean matching is that we'll always get a value within the range of observed values. Whereas if you use a theoretical distribution, like a normal distribution, you could get values that lie outside your observed range. So, and then for dichotomous variables, we're going to calculate a probability based on our observed values from a binomial distribution. So this is the basically the methods for doing multiple imputation. And so I wanted to give an example here of the different variables, or some of the different variables, and the amount of missing data that we had in the data set. And so here I have a set of variables. So here's demographics, age, sex, race, BMI, and we have comorbidities, history of heart failure, history of stroke, and so on. BNP and troponin are what are called biomarkers. And then the last set here is genetic variables. And so remember, we had 2755 total patients. And so this is the percentage of missing for each of these variables. And you can see it ranged from less than 1% to about 5.5% for 4 or 5% for some of the genetic variables. And so these are some more of the variables. So the magnetic resonance variables, left ventricular mass, right ventricular mass, and so on. The amount of missing is a little bit more. It's about 6%. And then this is the last three here, what's called morphology, about 4.5%, a little more. And you can see that in this case, the percent of missing is all the same, because a patient's value for these variables like mass and mass to volume ratio, ejection fraction, come from getting one scan. So if they're missing the scan, or missing one, then they're be missing all of these. And the same thing with morphology. So it turns out that for the variables that we were going to look at as far as predicting atrial fibrillation, all of them were missing less than 7%. So doing multiple imputation then would be a way of handling the missingness, because the missingness wasn't. I mean, it turns out to be extensive, because there are a number of patients that have missing values, but for any one variable, it was less than 7%. So what we're going to do, and I'm not going to go into any more detail on this, but what we do is that we build data sets that have no missing values using our imputation methods. And so I did 5 data sets where I imputed values to missing data in the order of how much missing there was. So I started out like with age and sex, which had less than 1%, and then I did another 5 where I randomly imputed without regard for how much missing there was. So I had ended up with 10 complete data sets. And then so every analysis that we're going to do, we perform 10 times. And then we estimate the regression coefficients by just averaging those over the 10 data sets. But then I've put this in for estimating standard errors to show you that it includes both within variance for each data set and between variance or variance between the data sets. Okay, so it turns out that for our analysis, there were some patients that were not were excluded, and there were 77 with permanent AFib, so those were excluded. And then it turns out there were 47 that had either no follow-up or a few that were missing values for all 46 variables. So that left us with 2631 patients for analysis. 96 of these patients had an AFib event for a total of 127 AF events, and there were 24 deaths from any cause in the follow-up time that we looked at. So we have 10 complete data sets. There's 2631 in each data set with complete data. And so we're going to analyze each one of those separately and then combine the results to get an estimate of the regression coefficients. So our outcome is a time to event. So we have atrial fibrillation, which is just yes or no. You either have the event or you don't. And then the time from enrollment in the study to the event. So our analysis is going to be Cox proportional hazards. And we have 46 potential predictors of atrial fibrillation. So now we have a lot of variables. And so the question is how are we going to select out of the 46, which are the best predictors of AFib? If we do ordinary regression, as you probably know, you really need more subjects than you have variables. And kind of a rule of thumb is you need about 10 to 20 subjects per variable. Ordinary least squares regression, as I mentioned earlier, relies on statistical significance for variable selection. That is, it does either forward selection or backward elimination, but that's based on a p-value that you set for either inclusion or excluding. A newer method for selecting variables, which you are seeing a lot more in the literature now because it is really an advantage to the forward-backward selection methods, is what's called penalized regression. And I'm not going to go into any detail on how this is done, but basically what we're doing with penalized regression is we're going to apply a penalty that shrinks regression coefficients towards 0. And so what we get then is a elimination of less important variables, and the more important variables sort of come to the surface as non-zero regression coefficients. And one of the kind of interesting things about penalized regression is it doesn't matter how many predictor variables you have in relation to your subject. In fact, you can even have more variables than you do subjects. So we have 46 demographic, clinical, echo, morphologic, CMR, genetic, and biomarker variables that we began with. And so we applied our penalized regression to each of the 10 imputed data sets. And then for each of the 10 data sets, we rank the variables according to their order of selection. And so for our initial model, we used the predictors that showed up in all 10 of our imputed data sets. And so this is probably more detail than anybody wants to see, but one thing I want to point out here, when we ranked the variables that they showed up as far as or appeared in each of our 10 data sets, you can see that index LA volume was always the first one in all 10, and contractile percent was the second one selected in all 10. After that, it's sort of varied, but it turns out that of the variables that were common to all 10 data sets turned out to be 11. And so these were the two that were always selected in all 10. The rest of these showed up and appeared in all 10 data sets, although not in necessarily the same order. So we chose these 11 variables to look at as far as predicting atrial fibrillation. The rest of these showed up less than 10 times, so we didn't include these in our initial regression equation. So our statistical analysis, I mentioned, is Cox proportional hazards regression. We did that for each imputed data set. But one of the other things that we needed to consider is the notion of a competing risk. And the reason for that is if you have a particular outcome, then to get the incident rate or the survival rate, there might be other events that would affect this. And in this case, death is considered a competing risk of atrial fibrillation. Because if a person dies, then they have no more chance of experiencing atrial fibrillation. Now, if they had an AFib before they died, then that's, we can count that. But if they died before experiencing an AFib event, then they're, in a sense, they're out of the consideration for having an AF event. So there's a method for dealing with that. However, it's also controversy regarding that. And I won't go into why that is. But so we compared the fine and gray method with just censoring at death. In other words, when we did the time to event Cox model, we just censored with death or censored at death. So then the estimate we're going to get is a regression coefficients, and then so what we're going to use is was a question that was asked earlier in the first hour, was we're going to use the information criteria, Kaiki's and Bayesian information criteria, to choose a best model. And so the next thing was to compare the competing risk model with the no competing risk, or just censoring at the time of death, or censoring when they died. And it turns out the regression coefficients were essentially the same. This is just for one of the data sets. I did this for all 10 of them. And you can see that the differences in the regression coefficients that we estimated were pretty small. So based on that, we then decided that we'll just do the Cox models and censor patients at the date of their death, rather than doing the competing risk model, because that's obviously more difficult to deal with. So we're then going to do the Cox proportional hazards model for all 10 data sets, censoring patients at either their time of death or when they were lost to follow up. So the another issue, and I think this is the final issue I had to deal with, is when we do survival analysis or time to event, the assumption of the Cox model is that hazards are proportional. And what we mean by that is that over time, the proportion or the ratio of the hazard rates are essentially the same. And you see this by looking at say the survival, a graph of the survival functions, and if they look like this, they're more or less parallel, then the hazards can be considered proportional. If the lines cross like this, then we have non-proportional hazards. That is, the hazard rate is not the same over the time period that we're looking at for different groups. So you can see there's a lot of issues that we had to think about in doing the analysis. So when we put this all together, and then of course we did a multiple event analysis as well as an analysis just to the first event. So we had 96 patients, as I mentioned, with 127 events. 85 had 1 event, 6 had 2, 2 had 3, and then there were 1 each with 6, 8, and 1 patient with 10 events. So, and I just wanted to give you an idea here of when you have a situation where you have multiple events, the data would be structured something like this, where for each patient you would have a start time, that is their either their entry into the study, which is time 0, and then when they have an AF event or whatever the event might be. So here, the first patient had an event at 12 months. So there's just one row for this, and this is an age, and MR is mitral regurgitation. So patient 2 here had an event at 15 months, and then at 27 months, they had a second event. So we have an indication here, I've called order. So they've had 2 events, and then patient 3 had 3 events, the first at 6 months, then at 18 months, and then at 31 months. And so that's how you organize data when you have multiple events. Okay, so then after we get our model, then we're going to look at model discrimination, which has an index that's called the C index. It ranges from 0.5 to 1, where 0.5 is none. You have no discrimination between those that experience the event and those that don't. And then calibration, we want to look at the agreement between the observed and predicted outcomes. And we do this by looking at a regression with slope equal to 1, or whatever the slope is, 1 being perfect calibration, meaning there's perfect agreement between the observed outcomes and the predicted outcomes, whether it's a mean or a probability or whatever it might be. So it turns out that in our analysis that the proportional hazard assumption was not met. And it turned out that age was the contributing factor to non-proportionality, as there were significant interactions of age with index, LA volume, LA is left atrial, contractile percent, and BMI. And so in our analyses, then we stratified by age. And out of the 11 variables that we started with, we wanted to then see if we could even reduce that to an even smaller set, because the smaller your model or the more parsimonious your model is, the better it is. But it has to predict, the reduced model has to predict as well as the full model. So we do this by what's called the likelihood ratio test, whether the reduced model is comparable to the full model as far as its ability to predict and discriminate. And I've given the formula here for the likelihood ratio test, which is the log likelihoods, the difference in log likelihoods times a -2, and that's distributed as a chi-square with degrees of freedom equal to the number of parameters in the larger model minus the number of parameters in the smaller model. I'll show you where that statistic shows up in the output. So it turns out that for all 10 data sets, if we look at just the time to the first event, then we have 5 variables in our model: BMI, index, LA volume, contractile percent, mitral regurgitation, and history of arrhythmia. And age, of course, is significant, but because it's non-proportional by age, then we're going to stratify by age. And so these other variables then were dropped from the model. The multiple event model included the same as the first event, except for the history of arrhythmia. And then, as I mentioned before, we estimate the regression coefficients for a single model by combining results over the 10 data sets. So here's the initial output for all the 11 variables that we started with. And so we have the number of subjects. This is time to first event, so we have 96 events. And we have this statistic here called the log likelihood, which I'll show you how that enters in a minute when we compare models. And so you can see that some of these are statistically significant, some are not. But what we want to do is we want to see if we can eliminate any of these variables here and still come up with a model that is just as good as this one. And we're going to do that by comparing these log likelihoods. So you have to make a decision on which ones you want to eliminate. So one way of doing this is taking the ones with the largest p-values here and eliminating those. So the history of afibrillation, we might take that out, or the reservoir percent. But basically what you're going to do is take out one at a time, see what you get, and then see if you can take out another one and then another one and come up with the most parsimonious model. So this is the model that I finally came up with, where we had 5 predictor variables. And you can see that this includes BMI, history of arrhythmia, contractile percent, left atrial volume, and mitral regurgitation. And you can see that history of arrhythmia here, although the p-value is not significant, if we take that out of the model, then it turns out that it's not as good as the model with it in the model. And so what we're going to do then is we're going to compare this reduced model with the model with 11 variables in it. So our -2 times the difference in log likelihood. So this is 345. You remember the other one was 342. We get a value of almost 6. And if we compute the chi-square that has 5 degrees of freedom, because we had we had 10 variables in the full model and only 5 here, so we have 5 degrees of freedom. So that turns out to be the p-value 0.46, so, or 0.47. So that tells us that this reduced model is just as good as the model with the well, I guess it'd be 10 variables because we're stratifying by age here. So so we can then use the reduced model here as our model, that our best model, and then we compute the regression coefficients by average over the 10 different data sets. So then another issue that we had to think about was then how do we present these results so that it's understandable. So because we're stratifying by age, one way of doing that is to break age up into groups. So you might do this by tertiles or quartiles or quintiles of age. We use what's called splines. I won't go into any great detail here, but it turned out that if we have a spline at with cutoffs at age 32, 52, and 62, which turned out to be the 10th, 50th, and 90th percentiles of the age distribution, then we used those age groups to plot our AFib-free functions for each of the variables in the model. And so this is a table of the different variables for the time to the first event. So what we have here are hazard ratios. And so what this means is, for example, like BMI, which is stated as 5 kilograms per meter squared. So it has an odds ratio, or a hazard ratio of 1.38. So what that means is that for every 5 units increase, for every 5 units increase in BMI, the probability of, or the hazards of experiencing an AFib event are increased by about 1.4 in the overall model. And then so what I did is to look at each of the age groups that we had. And so you can see that the for the youngest group here, although there aren't very many in there, very many events, the hazard ratio is actually over 2. So that means it's for the younger group that is the hazard for experiencing an AF event is increased by over 2. And then the same interpretation for the rest of the variables that are in our model. And then so the our overall model is pretty good. The C index is 0.75 and our calibration index is quite good, 0.94. So of course it's different and sometimes less or more or less for the different age groups, but this was included in the table to illustrate the differences of effect of the variables, BMI, volume, contractile percent, so on, by age. And so, for example, you can see here that for BMI has hardly any effect for the older patients. That the hazard ratio is essentially 1. So that means that there's really no effect for the older patients. And then this was the table for the multiple events. So that turns out to be fairly similar in terms of interpretation. Again, there's basically for overweight younger patients, there's a higher hazard or higher risk for an AFib event than for older patients. And by the time you get to 62 or over 62, there's hardly any impact at all. And so we then ended up showing graphs, which, as they say, a picture is worth 1,000 words. And so for a graph, survival graph for each, or not survival in this case, but AFib free for each age group. And so you can see that for BMI at the younger age, it's pretty similar, although as we saw, there was a bit of a drop the hazard for overweight younger patients. You can see more separation in the 33 to 52 and the 53 to 62. And then here is a plot of greater than 62. And so is the hazard ratio indicated that was nearly 1. You can see that there's hardly any effect of BMI on being AFib free. Since the curves overlap, the AFib free curves virtually overlap here. And then this was for volume. So again, at the younger age, there was hardly any difference here. You can see the big drop here if they have a high volume, left atrial volume, the AFib free is much less than it is for smaller values of volume. And this continues through the other age groups, although the effect is not quite so great for the older patients. And then for contractile percent, which is actually in the positive direction, the smaller the contractile percent, the worse is the greater the hazard for experiencing an AFib event. So here for contractile percent being 25%, you can see that there's greater hazard, and that really emphasize or shows up much greater in the older patients with a smaller contractile percent than the other age groups. And then I think finally, oh yes, and so finally what I end up with here is what is known as calibration plots. This is where I want to look at the observed versus the predicted. That helps to establish the validity of my model. And so you can see that for the different variables in my model, that there's really pretty good agreement between the observed, which are the solid lines, and the dotted, which are the predicted, and then for different values of, in this case, like BMI, I did less than 25% or greater than 30%. So you can, I mean, they're not perfect, but there's really pretty good overlap here between the observed and the predicted. So that gives you, I think, a flavor for how complicated and how any particular analysis can be when you want to do prediction of a particular event, whether it's in this case the event and time to event, or if you look at just events, an event in general that occurs in a particular time frame. So there's a lot of things that may have to be considered, and particularly when you have non-randomized studies, which is this is. So it can get quite complicated in the different things that you need to look at. You have to really pay attention to them. Whereas if you have a randomized study, then the statistics are pretty straightforward. They might involve time to event, but you would have just, you know, the time to event functions for one group versus the time to event functions for another group in a randomized study. Okay, so I will stop there. And I guess we want to take a break here. You want to take time for a few, are there any questions?
Yes, yes. So we have some questions in the chat.
Okay.
And I think since it comes from me, I'll make it easy for you. So I think on slide 38, that's a big, nice research. And I'm sure most of us would encounter that or would have encountered that and have used a simplified way, which might be a wrong way of doing it. So it would have been nice if even if it's simulated data, if you could make a simulated data available so that we can replicate the table on slide 38, which I think I've come across that, and I didn't do it the way you did it. Most of my economists are also struggling with variable selection as far as the big data goes.
Okay, on variable selection. Okay, so
yes, slide 38.
Yeah.
So you basically systematically indicated that there were some variables that showed up in all 10 models, but it's difficult to replicate what you've done. Understandably, the data is confidential, so you can't share much. But if there's a way that we have a lot of data sets in Python and R, we have the Titanic and the Flight data set. We could use that to replicate slide 38. I think maybe in a later model that would be very, very educative.
Okay.
In my view.
Yeah. Right. So the variable selection model that I used, well, I've actually used two. There's one in Stata, and then there's another one in R. R is probably the better one, or you get more information, more detail on that. So, but it basically it comes down to you still have to make some decision yourself. It's like you can't just run statistics and without thinking about it.
Yes.
Yeah. So, okay. So I will create some data and to do a variable selection.
And then there's also a paper. So there's a paper that I linked, which is incidentally written in R, and that paper, maybe if you take a look at that, it will make life easy. And but if you come up with your own example too, that would be great. So there's this paper that has the data set. They didn't do. He went with the BIC, but it would be nice to do it, to have an alternative systematic way of doing it. Thank you very much.
Okay, so we'll do a break, and then you'll get into the examples that we have. Okay.
Yes. Okay. Thank you very much. And for those, I mean, I'm very sure everyone is going to stay for the coding part, but please make sure your code. I mean, you clone what we have on GitLab. I mean, GitHub. We use GitLab tenants. So sorry for that. So clone what we have on in GitHub so that your working environment is up to date. And if you're using Codio, the Codio files are up to date, so it should be fine. Yeah,
excuse me, I saw another question here about timeline to develop a model. So that really varies. This was quite complex, so this took quite a bit of time. I can't remember exactly how many months, but it would have taken probably 3 to 4 months to develop that. And then after I actually developed the model, the PIs, the principal investigators thought, oh, you know what, we left out a variable. So I had to do everything all over again. So, you know, things like that happen, you know, too. But yeah, it's not just a matter of you know, a couple of days. It takes some time to you know, to go through all of that to develop a good model. Okay.
Okay. Thanks, Paul. Okay, John. So are we at a good stopping point, and when do we come back?
Yeah, we can take spot 5 minutes to 1, so we can come back 1:10.
Okay.
Yeah, let's reconvene at 1:10.
Okay. Thank you. We'll see everyone at 1:10. Hello? Yes, can you all hear me? Can anyone hear me?
Yes, sir.
Oh, good, good. Okay, so we give folks a little bit time to, maybe 2 minutes, and then we'll jump on. Okay, for everyone, I can't see my video well, so I'm driving blind here, so I can't see my video screen for some reason. So if you can't see me, just let me know. I see the chat, but I don't see myself. So what we're going to try and do is to make sure that you all have the files from GitHub. So if you don't have it already, if you haven't done that before, or if you're struggling with that, you go to the link I have in the chat, and two options. You can either click on the code part, or sorry, when you get there, you primarily get to the root, right? You get to 2020, and you hit the code, and you have two options. You can either download a zip and uncompress, or you can just copy this, and then once you are on your computer, you go to the location where the file you want, the location where you work from. Okay, so if you look at mine, what I have here is that in my 2022, I have my GitHub, which is like the virgin copy of the file. Because the thing with the GitHub is, if you work off your GitHub directory, then the next time you try to pull, it's going to tell you that you have new files that are not available in there. So it's not going to write over it. And then I have my personal. Okay, so personal is also a copy of Git, but this one here, I manually put the files in. Okay, so these are the files that I work on. Okay, so here I don't do a git pull. I just do a git clone here one time. And then the subsequent times I just go to this location and manually copy the files, the new folders, and put it on the other one. Okay, so primarily that's what you want to do. What I mean is, if I come down here, remember from the earlier lecture, and you go down here, you can see git bash. And then once git bash comes, you can do a git pull. This time it's not clone, it's a pull. And if all goes well, it should bring the data. So it tells me it's up to date, so I'm fine. Okay, so that's the first thing you want to do. So we give everyone a minute to try that out. And then once you have it, then you open your Anaconda and point to this directory, the 3D directory. And then there will be a file in there called mod3b day 1-2 exercise. Okay, so that's what we want to open. If you open that, then you will get something that looks like, so let me kill this guy and kill this guy. You will have something that looks like this here. Okay, so primarily, you have this open one of the files, and in your case, you are going to open the exercise. Okay, how do you know is the one that we want? You see that it's code along student file. Okay, there will be a solution file in the solutions. As usual, when you get stuck, you just look at the solution file. You work on the student file, and I will demo using the instructor file. Okay, and the instructor file tells you here. So why don't we take 5 minutes? Everybody, make sure you have your file where you have your files open, and then we move on. In Codio, it's the same. You go to your Codio folder, and then when you click on the file that says exercise more 3B day 1-2 exercise, and that will give you something that looks like this. Always look for the student. It will tell you whether it's a student file or it is. So there's a student file. So we take 5 minutes, and then we come back. So get yourself to the state, and then we should be all set. If you're on your personal laptop, then run this portion. Okay, take out the exit. Okay, put a pound at the exit. If you're on Codio, don't do that. So on Codio, don't do that. So let me move this out of the way so I don't confuse the Codio guys. The Codio guys, you're all set. The non-Codio guys, you click on the libraries, and then in here you put a pound, and then run it. Okay, and run your segment. And so we take 5 minutes and get back. Okay, so I think everyone, we are on track, right? If you have any qualifiers for the, yes, is there any example of, yes, there are examples. So if you look in here, okay, you see that there are two files, the IPYNB, okay, the 3A is for last week, okay, it's what we did last week, and the 3B is what we're going to do today. Okay, so this is my personal. So yeah, we're going to work off the IPYNB, IPython notebook in mode 3B. B. It's not 3. Okay, so 3 was last week. We want the 3B, like ball. Okay, so let me emphasize that if you go to just mod 3, you won't find anything. You have to be in the mod 3B, like ball. Okay, so check out the GitHub. I made that clear, but if you didn't catch that, yeah. So if you go here, you see there is a mod 3 and there is a mod 3B, like ball. And that is 5 hours ago. This is 7 days, so that's 1 week. You want this folder, okay? And then these are the two files that you want to open. Okay, so in the interest of time, let's keep going. Okay, so primarily what we're going to do here is you have your file open. We're going to try and mimic most of the tables that Paul had gracefully provided, the data, and I give you the slide number and things like that. So specifically, if you take a look at this slide, okay, this is what Paul used. If you go a little up, you see things like that. And so we want to replicate these models and these tables in Python. Okay, so that's what we're going to do. So you load your libraries. And then once you finish loading them, you put back the exit so that next time you run, it doesn't reload. I mean, because the install takes time. Okay, so then this part here is just a warm up, just to recall what Dr. Musa did with us, what the different types of Python data types are. Okay, so just take a look at how the data types are, because we'll need this as we move along. We need to know how to create a string. We need to know how to create an integer, a float. Okay, so these are just here, FYI. Okay, so if you run this, you see an output. What I look out for is how to display my result, how to create a data frame, how to create a dictionary, and things like that. And how to play with the import, because we're going to use a lot of math functions. So where those functions are. So if you take the ln, the natural log, it's in the math function. If you want the power, it's in the numpy, okay? And then you can compute some values and print those values. Okay, so that's what we're doing in here. Recall that if you don't have certain libraries, you're going to get an error. I have the numpy in my environment, so it's not going to give me any problem. If you, on the other hand, this is the first time you're doing that, then you may want to, after you install, you may want to import. Okay, you may want to bring in these the libraries that you would use. So you bring in something like numpy and pandas from Dr. Musa's class. Okay, so run this, and you'll get something like that. Don't worry, if you didn't get an error, just as a warning, then you'll be able to run this. Okay, so then you'll be able to run this portion and observe the output. So this is just observation. And then the actual task starts here. Okay, you have 5 tasks for today. And so please just follow this and just fill in those, the ... has to be filled in. I've given you the output. So primarily I have a list and I want to create a data frame out of it and display it. If you do it right, you get this output. Okay. If you struggle with it, then you go to the solution. Okay, so just go to the solution and you would have the solution in here. Okay, if you're on Cordio, the solution has been separated. The solution has been moved into another folder. So you would click this one and you'll see that it's an instructor, and then it tells you how, or you can even run it in the instructor window, and you will get primarily an output along. So for this one, for the first one, I'm just going to show you what I wanted. So I want something like this. So I want you to take this skeleton that you saw in here, okay, and turn it into something like this, so that when you hit run, you get an output. I'm sorry, I didn't do it right. And that's the thing. If you, for some reason, if you see yourself popping around, just go up and click on here, and it will take you right there. You can go back using this hyperlink, okay? And so I'm here, and I'll just run. And you see, you got a PD. That means I haven't loaded. So I will put it here, run, and in the instructor, if you get an error, that's primarily what it is. Okay, because I've tested it. Okay, cool. So that is what I want. We want you to try. And once you go through this, we'll be able to create these tables that are on Paul's slides. All these tables and outputs, we'll get them exactly. But you need to learn how to get into it. So yeah, so we take ourselves, we said we'll give everyone like 15 minutes to complete. After we come back in 15 minutes, then we would ask you to, we'll pick one or two people and say, hey, how did you do it? What are the struggles you did? But the assignments or the in-class exams, they are very clearly labeled, 2 of 15. And for day one, you're only doing 5 of 15, 3 of 15, 4 of 15, 5 of 15, okay? And once you finish, if you want, you can keep going on, but at this point, you can just stop. Okay, so once you get to 5 of 15, then you basically have ended, and you wait and we'll come back. So John, so we'll say we'll come back at 1:45 to the hour. And if you have any questions, please put it in the chat, and I would we'll come to you. Any questions, any challenges? Is it a good way of doing it? Is it a good way of spending your time? I'll say yes. If you don't try things out, you won't be able to. And I've taken time, trust me, myself, Paul, we've really, and the whole group, we've taken time to make sure that you don't get stuck. So if you see yourself getting stuck, just go to the solution and just, you can copy it from there and paste it. But going through would help, please. So we call ourselves off at this point. It's almost 1:28. We'll come back, let's say at 1:45. Okay, John, is that a good idea? Paul? And Nana?
Yeah,
Yes, is that a good idea?
yeah, that's fine. So,
Okay, cool. And Quincy, yes. Okay, we'll come back at 1:45, please. And put your items in there, and we'll address them. See you at 1:45. Mm. Okay, folks, I think we're getting ready. We have just about 3 minutes, and then and we'll be there. So be wrapping up. Yeah. So there's okay. So we have 2 more minutes, and we'll get back. Okay, folks, let's get on it so that we have enough time for this exciting. So in here, if I will call on let's say Bizarre, if you don't mind, was it challenging? Is it something that you applied? Some of the skills you learned in class, did you have to do a lot of cross-referencing? These are the type of questions we need to know. Were you able to just observe it and say, hey, you know what, I've seen this before? And anyone at all, you can. If you can't respond, just put it in the chat. But I know Bizard, so I'll just call Bizard. BEHZAD. Okay, so what about Francis? Pick any of the 5 questions. Give me any of the 5 questions. How was it? Was it difficult? Was it? How did you approach it? Which ones were they easy to crack? Not, and these are the type of things you would encounter as you move into the Python programming. You pick and choose your 5, and then you build on it. So, can anyone please jump in here? Okay. So then let's do it this way. Can anyone hear me?
Yes.
Okay, cool. Okay, then we do it this way. We go straight to the questions, and then we'll look at the solution. So here we're saying we want a data frame that looks like this. Now you have primarily a list, and how do I know it's a list? The square bracket, right? So you have 2 lists, and you want to turn it into a data frame. We know that in the data frame, a data frame takes a dictionary. It also takes it can take a list, but you have to format the list. So how would you work this out? So the way to work this out is primarily to say that, hey, you know what? I have a name. Okay, so you just say, I got a name called name. Okay, but the name is going to be the column name. So let's say call name. Let's say name call. So let's change it so that we know. And then it's the variable name. Okay, because the variable name will be assigned. And then we'll do the same thing for the score. We just say score equals score. Okay, so we take this here, Control C, and stick it here, Control V. Okay, and primarily you just say score equals to score, and take this out, and then you put this here and put this here. And then if you run and it doesn't come up, then you so primarily what I'll do is I'll comment this and comment this just to make sure that it works before I go on. Okay, so now it's saying, hey, you know what, you didn't do it right, and there's a point at which you would then go to the solution and take a look and see how it's done. Okay, so you will take a look at here and see how it's done. So if we take a look at it, what did we do wrong? You have to primarily a dictionary, right? You are creating a dictionary. A dictionary is a key value. If you remember from Samusa, so you come down here, and in the interest of time, all you do is you just take this and put it in here. So I'm just showing you how, if I were you, I'll do it at home. Okay, like that. You take a baby step, and then you run and say, good, I got it. Then you come in here and say, well, you know what, I got it, but let me see what came out. And that's why you make a free cell. Okay, you make a free cell and put it in it, and then run it and see what comes out, and it's a dictionary. So now at this point here, you say, hey, you know what, I know I can get a data frame. So it's basically a data frame, and this doesn't have a code completion. So it does have a code. It took a long time. A tab will bring it. Okay, data frame. Okay, and like that. Okay, even the code completion isn't very good. Okay, sure. So you put this here and put your dictionary in there. And once you do that, I'll do baby step still. No error, and then I display it. And then I got success. assuming, there we go, I had a comment. So, and this is how I would do it. Take your time, do baby steps. So that's task 1. And so in the interest of time, I'm not going to waste time. We'll go through task 2, 3, 4, and 5. Now task 2, primarily what we want is, so in here, you just run this and you get it. The reason we're doing this is we want to have data in memory. To be able to do anything, the data has to move from this to memory, or you have to somehow put the data in memory. What do we mean by data in memory? To have data in memory, we have in here, you don't see it very well, but if you have other IDs, I have a VS Code, okay? Now in VS Code, what I mean by data in memory is that I can do something like, should go up, good. So this is the instructor, yeah. And I'll go to day 1, day 1 here, okay? And you can, if I run this portion here, okay, in VS Code, PD hasn't been loaded, so I have to do, remember what we have to do? We have to get that, we have to get that little piece of code that says, hey, bring this and bring this. Okay, so we have to go here and come down here and throw that in to get the error out. So we go down here, I insert a code, and this is just like any other notebook that you can use. Okay, but I want to show you what I mean by, and that's the output. And I like playing with IDs. The reason being that you want to pick the best ID. That in here, see you have variables. If I click here, I can see my variables. This is what most Python IDs lack that VS Code has. Okay, so VS Code, I can easily see the variable if I have it nicely. There we go. I can see the variable. I don't have to go outside. Okay, so that is one cool thing. Yeah, so I can see my variable. Okay, so that is one cool thing that VS Code offers that other ones don't. Okay, and so if I come in here, there we go back. This just for FYI. So I'm going to go back to the main one. So the main one, we've seen how to get data into memory. Now we're going to get more data into memory. Okay, so more data into memory. If you recall on slide 10 of Paul's, so I'll go down here and get the slide 10. Okay, you got the slide 10 from Paul. It should look something like this. Oh, sorry. It should look like this, and then you just go to slide 10. Okay, this says slide 10. You go to slide 10, and if I got my slide number right, I think this says, oh, the 412. Yes, that's the second one. So if you go to the 412, which will be what will be taught tomorrow, you would have that. Okay, so this is the 4110. Okay, that's what the slide implies. Okay, so I just want to show you this. And then for those who didn't get opportunity to go through this, when you get home, you do it. For day 1, we're just getting the data in memory. Okay, so we go to slide 10. I think it's said here. Okay, this one. Okay, so you have something like this. This is going to be an assignment that Paul is going to do tomorrow, but how do you get the data in memory? And that is what we show in here. Okay, so you get the data by just taking the row, putting it into a table, which is just a continuation of what you did from here. Okay, and then once you have a table, you know how to get into a data frame, taking the table and sticking it into the data frame. So if you run this, then you get that, which looks almost the same as that. 34. I mean, it will look very similar to something like that. Okay, now you got the data in memory, and you can do some more. Okay, so we'll go to task 3, computing the confidence interval. To compute confidence interval, this is just FYI. You would need a formula, and once the formula is given, you just have to compute it. Okay, so this is how you compute it. The easy part you assign easily. The most challenging part you do systematically. Okay, so this is how I will compute my confidence interval. And so here, if I were you, what I'll do is I'll take one of these guys, do plus, go to the cell and see how that comes out. This I want to do this guy. Okay, so you take this, Control C, Control V, and see how, and come on. Okay, so that gives you the exponent of that. And for the ln, you do the same. I mean, you import these guys, okay, Control V, and Control Enter, and then see how you do the ln, the natural log of this guy. Okay, so you pick your phi, make it easy to, and so if I'm able to do this, then of course I'll be able to compute this and compute that. Okay, so I'll be able to compute this here, Control V, and just run that. Okay, so I've gotten that, and I'll be able to print it. Okay, Control C, and just put it back in here, and run, and you get an output. Okay, so your task will be for tomorrow will be to get this other half as well. So that's why I left it out. Okay, so that is what this is doing. Then once you pick your phi, you come back and you do this and you run. Okay, so we are running out of time, so let's keep going. So do that for exercise 4, the same way. We want to just see how to visualize, how to get data. So at times the data will be in Python itself. So the way to get data is to load a library that has data in it. And this is how you query a library that has data. The Seaborn package has data in it, okay? So if I import Seaborn, I can then look at the data that is in Seaborn. And to do that, you do Seaborn data set, okay? If you do the Seaborn data set, it will tell you what the data you have in that package. And so that's what this is doing. Okay, Control Enter. And those are the data sets. So I can then say that from the Seaborn data set, load the Titanic data and give me a head of it. Okay, so that's what this is doing. And you get that data. Okay, so we've done that. And the next one is the data exploration. This is the coolest part of it. So when you get home, please try this. You have data, you want to see if you have missing data. What else do you have? So in here, all you do is you take out this guy, okay, do baby step. Just run this guy. We know how to load the data. And then once you load the data, you can then do like a head of the data, okay? df.head, okay? Inspect the data before. We are running out of time. So, oh, shoot, sorry. Sorry. Yeah, head of df.head, okay? Inspect the data, and then you can profile the data. If you profile the data, this will take time, but let me show you how it's going to behave. If you run this, you're going to get something that looks like this, okay, to run through, and it's going to pop up something on your screen, and that thing that's going to pop up will look something similar to this. And this would allow you to do all sorts of analysis on your data. You can look at missing data, okay? You can do a whole lot of other things on the data. And that's what I want you to explore. So for today, it's primarily exploratory. Go through, there are 2 types of exploratory data analysis free packages that you can utilize. It's called the Pandas profile, okay? And the other one is this other one. So this might take time, so let me stop that, but try it out. The other one is this second portion, which is the data table, okay? So for the data table, that is what pops up here, to pop up in your browser and just go through and observe what comes out, okay? So like here, I can look at, if it's float, you can have something like that, okay? It tells you that most of, you have some outlier in your data, okay? And things like that. So please, we are on the spot to give ourselves time to do the survey. We'll stop here. When you go home, try and go through the exercise for day 1. And then day 2, we'll do the second portion of it, okay, which would be as you go up the student file, the day 2 will be this portion. Okay, and the day 2 will take us through the table. Day 1, getting data, exploring data due to getting the tables that Paul did. So thank you very much, and I pass you back to Paul, to John and Stacy.
Yeah, thank you again, Paul and William, for another excellent presentation, and thank you all for participating in this training. We're going to meet again tomorrow and then continue with the statistics. But before you leave, if you haven't signed in the sign-in sheet for attendance, please do so. And I believe there will also be TA session this afternoon. Is that right, William?
Yeah, Ibel, and I think I missed Saturday, so I'll hang in. I'll help Ibel today. Yes.
Okay, yeah, so from 4 to 5, TA sessions today. Yeah.
Okay, sure. Okay, and please try this tool. This tool is really very good. Okay. Yeah, thank you very much. And
all right, so thank you all again, and then we'll see you all tomorrow, same time.
Thank you. Yeah, someone is asking where the sign-up sheet is. So, Stacy, if you could please either put it in the Slack or
in the chat area. You check the chat area, it's there, or you can check that in Slack.
Yeah. Okay, thanks so much. Thanks a lot.